Okay, this is Physics 1A for April 28th. Today we're going to talk about some more applications of circular motion. We learned last time about this definition over here of radial acceleration, where if you know what the velocity of the object is and you know the radius of the circular path that it's traveling on, you can find what its radial acceleration at a moment in time is by using this equation right here. And we're going to use that to solve two problems. And then after we're done with that, we're going to talk about this lab manual assignment that I gave to you. So here's the first problem. So we have a Jeep, which is shown in this picture here. It says we want to find the maximum speed that the Jeep shown can make a circular turn with a radius of 50 feet without tipping over. And we want to assume that the road is level and that there's enough friction. So what we're looking at here is the back of a car. So the car is traveling into the screen. And we want to figure out how fast it can go before it starts to tip over. And let's say that it's traveling, if we looked at an overhead view, let's say that it's traveling around a circular path. So around a path that looks maybe something like this. And I guess the first question to ask is, if you're in a car, like a Jeep that's really top heavy, or has a high center of gravity, which means that it has a potential to tip over, if you're traveling in this direction and you're turning to the left, I guess the first question to ask is, if you go too fast, which way is your car going to tip or roll? Is it going to roll to the right or is it going to roll to the left if you go too fast? Everyone's saying to the right. Does anyone think it's going to roll to the left? What's the reason that you know it's going to that's going to roll to the right? Due to inertia. Centrifugal force is got to be a little bit careful with that phrase, but I think that it's consistent with well, it's just there's two words and they mean different things. So there's centripetal and centrifugal. And I try not to use the second one ever because I don't really understand what it means. Centripetal is just the acceleration or the direction pointing toward the center. This thing is actually tipping in the opposite direction, so it's not centripetal. Centrifugal is definitely the word you're looking for. Not centrifugal. I don't think that's a word. Centrifugal. Centrifugal that's what you're trying to say. Centrifugal, centrifugal. So this would be pronounced either centrifugal or centrifugal. I don't know how to pronounce it. I try not to use this word very much. This is what's called a pseudo force or a fake force, I guess. Again, I really just never use this word because I don't understand the right way to use it personally. But yeah, I think in this situation people would say, oh, what's the force that makes you actually tip? And the answer would be centrifugal force. Now that's not true. What we're going to find out is actually the friction force that makes you tip. And it's really inertia that makes you tip. Because if you're traveling in a straight line and then you try to turn to the left, your car still wants to keep going in a straight line due to inertia. And that's really what makes it roll. You could call it an inertial force if you want to. I've seen people use that expression before. But again, it's not really a force. I mean, what is a force? That's really the problem with all of this is you have to really identify what a force is. And for me, in Physics 1A, when I'm talking about forces, I try to stick to forces that are like real, which are things like friction, tension, gravity, electricity, magnetism, like real forces. But there's also these things called pseudo forces, which are forces that appear when you have something else that's happening in the system, okay? And a really good example of this, I don't know why we didn't talk about this yesterday, occurs in that kind of carnival ride where you are, God, this looks awful. Those kind of carnival rides where you are standing on like the inside surface of a cylinder, and then the entire cylinder is rotating. I'm sure many of you have ridden rides like this before, right? Where they might put you in a cage or they might put you up against a wall or something like that, but then the whole thing spins And what happens is that your body basically gets pressed into the wall, right? And the faster that it spins, the harder that your body gets pressed into the wall, right? Now, when this, like in a washer, right? Yeah, like in a washer or a dryer where when it's spinning, all of the clothes basically go to the outside wall. Yeah, the washer's a better example because, yeah, it's a horizontal spin, right? And all of the clothes get pressed up against the wall. Yeah, so you could ask the question, like in the washer or in this type of a ride, what is it that you're feeling? What force are you feeling when you feel yourself pushed into the wall? And there's really kind of two answers. So what is the answer? What is the force that you're feeling? Andrew says the momentum going towards the wall. What force is it? What force is it? If you were to name a force that we've learned about, what force would it be? Yeah, velocity isn't a force, though, right? It's a normal force, that's right. So if you were to draw the free body diagram for this person right here, you'd say, okay, well, let's say they're on the edge there. There'd be a normal force pointing this way, right? There would be probably some type of a friction force holding them up, and their weight would be pointing down. And that would be consistent with what's happening for the acceleration too, because the centripetal acceleration would point toward the center. And then you could actually say, oh, well, what is it you're feeling when you push into the wall? You're actually feeling the normal force of the wall, which means that you're feeling the wall push on you, right? And it almost feels kind of like a secondary kind of weight, right? Because it's the same sensation you get if you're in like an elevator and the elevator starts to accelerate upwards, right? You feel it because the force from the floor is pushing on you, and it makes you feel heavier, right? So for me, at least, when I first rode one of these rides and I got pushed up against the wall, for me, it almost felt like gravity was pulling me towards the wall, And I think that's where people come up with this concept of a centrifugal force or of a pseudo force. And I think that's what they mean when they centrifugal force. They say, oh, I'll hear people say, like, due to the centrifugal force, you're pushed against the wall. That's another explanation I've heard of this kind of stuff. And I used to think, quite naively, when I was studying physics, that was an incorrect way to describe what was happening. And then I started hearing extremely bright and intelligent physicists start to use that expression. And so then that's where, like, I get kind of this question of, like, what's real and what's not real. Because ultimately, what we're doing is we're describing what's happening. And if there's two different ways... Now, physics is logical. Quantum mechanics may not be logical, but most of physics is logical. What I'm trying to say is that because of the type of, like, things that we're trying to explain can be... We don't really always have the exact right words for them. Maybe our mathematics is really good for them, but sometimes the words we use aren't really great for them. I think that... And also because the concept of what a force is it's not... I mean, it's well-defined. Like, we can say that a force is an interaction between two objects, but then what are the two objects if it's a centrifugal force? If we say there's a centrifugal force that's pushing this person outwards, or... Yeah, like... What are the two objects then, If it's a centrifugal force. Isn't it just you? Does that make sense? Like, if I put a box on a table, and I say that this box has a weight, well, Newton's third law tells me that every object, every force that we can describe has two objects. And you can describe the force of x on y and the force of y on x, right? So if I say this object has a weight, what I'm really saying is that the Earth puts a force on it called weight, and this box technically pulls back on the Earth with the same force, right? If you have two people that are pulling each other in a tug of war, one person pulls one way, the other person is the other way. So you have two things. But when you use the expression centrifugal force and you say, oh, this person is thrown to the outside because of a centrifugal force, or if you say, oh, I have a basketball in the back of my car, and when I go around a turn, the basketball goes to the right, and I ask, why did the basketball go to the right? And someone says the answer is because of the centrifugal force. Well, what are the two objects for the centrifugal force? You know what I mean? It's the basketball and what? What's the thing that feels the reverse force? Does anyone have an answer for that question? But you see the problem, right? So that's where I'm like, I don't really know what it means. So they use the expression pseudo force. And pseudo force also applies to some other situations. So for example, the Coriolis effect on Earth, which is the effect where something traveling in a straight line on Earth will tend to be deflected. That Coriolis effect is considered to be a pseudo force as well. So yeah, this is like definitely something that I try not to use these expressions at all. So you're not going to hear me say centrifugal ever again. I'm just kind of talking about the way people talk about it. I'm sure like a really bright physicist watching this could pick apart all the things that I'm saying. And I'd love to have a conversation with someone that really does understand the right way to say these words, so I could learn more about it. But no, most of the physicists that I meet don't really use it. You know, most of the people that I work with, for example, throughout my life haven't been the type of people that have used this expression. It's just usually when I'm watching like a YouTube video that I'm like, wow, this person's really smart. They know a lot about cosmology and quantum mechanics and all that stuff, but they still use the word centrifugal force. And I'm just like, it kind of like bothers me a little bit, but then it also feels like maybe I'm the one that doesn't really know things, you know? I'm just a physics professor at a community college, you know? Like, what do I know, right? But I try to stick with what I do know, which is that using centrifugal can get kind of weird. So I try not to use that, and I try to go more for the quote real forces, like the normal force is the thing that actually is what's happening here. Because then I can teach, right? I can only teach you what I understand, right? I can't teach you what I don't understand. All right, so that was a bit of an aside, but it is something that is worth talking about because you're certainly going to see it in literature, whether it be physics textbooks, YouTube, whatever. All right, let's get back to this problem. So car traveling into the screen, and we just figured out that it's going to want to tip to the right. So our question is, how fast can it take this turn where the radius of the turn is 50 feet? And again, that means basically that you're turning through a circular path where the radius of that path is about 50 feet. We'll call it R. And the velocity of the car is v. So in order to analyze this, just like we do with most problems, we're going to need to draw a free body diagram. I think I can pretty safely draw the free body diagram on the picture right here. What are the forces that this Jeep is going to experience? Normal weight friction, right? Okay, now, since we all agree that it's going to tend to tip to the right, is it okay if I draw the forces on the right wheel and just kind of assume that the left wheel might be just like barely lifting off the ground as it makes the turn? Because it can make the turn and not tip if the wheel kind of lifts a little bit as it makes the turn, right? Like, that's totally acceptable. So we'll put all the forces over here on the right side, and this is pretty consistent with some problems that we had done early on in this class that were like asking the question of, you know, when is something going to tip, right? When is an object going to tip over? And we use the same kind of like idea. Okay, so we put the friction force right there, and we're going to put the normal force right here. A little hard to see with all those dots on there, but so there's the normal force. And then we also have to have a vector for the weight, and that's going to come, the center of gravity, that's what CG stands for here, is right in the middle of the object right there, or right there at 3 feet above the ground, and then 7.2 feet between these 2 points right here. Okay, so that's all the information that we have so far. And we need to figure out how fast it can go without tipping, right? So all we can really do in analyzing this problem is kind of think about the information that we're given. Now, we can say that if it's turning to the left, I would say that the direction of the centripetal acceleration vector is going to go this way, which means that that's going to be the positive radial direction. That's going to be positive r, and we'll make up to be positive y. if we do that, we can write down an expression that the net force acting in that radial direction will be equal to the mass of the object times its acceleration in the radial direction. There's only one force acting along the radial direction, that's friction. So that means the friction is going to be the thing that's providing the central force. So we get that expression. And then we need another equation, right? And one of the equations that we could use would be net force in the y direction would be equal to 0, which means that the normal force should be equal to the weight, right? But that doesn't really tell us any new information, because our goal is to find the size of the velocity. And all we know is that there is enough friction, which means we don't really know how big the friction force is. We just know that no matter what happens in this problem, this Jeep is never going to slide, right? One possibility for the motion of this Jeep would be that it tries to make the turn, but let's say that its tires just lose grip with the road and it just kind of skids off in that direction. That's one possibility. But it's telling us that's not going to happen in this particular problem. It's saying that there is enough friction on the road. It's a very dry day maybe, and the tires have really good solid grip. You know, they're not old, they're newer tires. So it's not going to skid. But that doesn't tell us how big the friction force is, you know? Like, we can't really directly calculate this. So this equation really still has two unknowns. So what we need is another equation. No, you can't just make it 1. We can't just make it 1. So this is a type of static friction. And if you remember the way static friction works, it has like a threshold. So I assume what you're meaning, Bran, is that you'd want to make mu s equal to 1, which we could do, but that doesn't mean that we would know the friction force, because the friction force would still always be less than or equal to the normal force in that case. So we could make it equal to the weight, and we could solve for the velocity then, but that wouldn't really solve the problem for us, because it's because of this less than or equal sign. All we know is that the friction could be as big as we need it to be, but we don't know what the value is, and we would need to know the value if we wanted to find the velocity. We also, by the way, do not have the mass. So, what other equation can we maybe use in this problem then? Something that uses the dimensions. Yeah, exactly. We need to use that 7.2 feet and the 3 feet somehow, right? What would it be? Can anyone think of another condition that we can place on this Jeep as it's making this turn? Yeah, torque. That's right, torque. It's tending to roll, but we don't really want it to roll, right? So what would it mean if it didn't roll? Well, that would mean that it stays in equilibrium. And the only way that's going to happen is if the sum of all torques is equal to 0. Now, if the torque that's rolling it in this direction is greater than the torque that's rolling it in the other direction, then it's going to roll, right? It's going to flip. But if the torque that's going to the clockwise direction is the same as the torque that's going to the counterclockwise direction, then it's not going to flip. So that is the second equation that we need here, or third equation. I don't think we're actually going to use this one. Okay, now, to use the torque equation, what do we need to do before we can even start using it? Set a pivot. That's right. So what are we going to use for the pivot point, or the axis of rotation? What's a good point to choose? Okay, so if we pick this point right here, then the friction force and the normal force are going to cancel out of our torque equation, right? Like, if we pick that point, we're going to have n times 0 plus f times 0 plus weight times, I guess, would be the lever arm, right? 3.6. And this isn't going to work. We can't really solve for anything now, because if this is 0 and this is 0, we just get w times 3.6 equal to 0. It's only going to work if the weight is 0. This equation doesn't actually give us any new information, right? So we can't really choose that one. What else can we choose? Center of gravity. Let's try that one. Let's see if that works. So if we choose the center of gravity right here, to be our axis of rotation. God, that looks awful on this screen. If we make that our axis of rotation, now, yeah, the weight won't show up, but we can write, let's see, let's make positive, let's make clockwise positive. Whoops. Clockwise positive. So if we make clockwise to be positive, then we'll have F times the lever arm, which would be 3 feet, minus the friction force. Oh, no. I'm sorry. The lever arm for the friction force. Oh yeah, it is 3 feet. And then minus the normal force. And now we need the lever arm for that one, which is going to be half this distance. So 3.6 feet. And now we can get a relationship. I guess we can plug in the weight right here. So N is equal to the weight, but weight is equal to M times G. So what we can do here is we can say F times 3 feet is equal to mg times 3.6 feet. And then we can use this equation to replace the friction force. So we'll have mv squared over r times 3 feet is equal to mg times 3.6 feet. And now I think we can solve for velocity. The masses cancel. Our velocity is going to end up being equal to r times g multiplied by 3.6 divided by 3 is going to be like 1.2, I think. Right? Check to see if that's right or wrong. So that appears to be our maximum speed. I didn't write it. This is the max speed. And to calculate that, we have a radius of 50 feet. We have an acceleration due to gravity of 32 feet per second squared. Can't use 9.8 unless we convert 50 feet into meters, and I don't see really any reason to do that. And we multiply that times 1.2, and so we get Vmax, whatever all this ends up being equal to. You want to tell me what it's equal to? It's the square root of 1920. Okay. So it's about 44 feet per second, huh? Which I think we calculated last time was something like 60, no, not 60, 30 miles an hour, right? There we go. Any questions? So ultimately, the thing that really determined how fast this person could go was basically kind of like the ratio of the width to the height. So notice that 3.6 feet is like equal to half of the width of the object, right? And 3 feet was equal to the height. Not the height, but the, you know, the y coordinate of the, let's call it the center of gravity. So basically the ratio of this divided by this leads to really all that really matters in terms of how fast you can take the turn, because you can't really control the size of the turn. Now, what this means is you could take a wider turn much faster, right? If the turn had a size of 200 feet, for example, a very gradual kind of curve, then you could go twice as fast, right? If this was 200, the answer would have been 88. So that's pretty obvious there, right? The wider the turn, the faster you can take it. That's not too surprising. If you're on a straight road, which has no curvature, then the curvature is effectively infinite. Sorry. Yeah, the curvature is basically infinite, which means that the velocity would be infinity as well. So you could go as fast as you want on a straight curve. That's consistent with what this says. And you could also go faster if gravity was heavier. So if it was a different planet like Jupiter and we had roads on Jupiter somehow. But yeah, anyway, it's mostly just the ratio of the coordinate of the center of mass, or the width divided by the location of the center of mass. So basically, the smaller that this is, the lower to the ground that the center of gravity is, the less likely it's going to tip, right? Which is also pretty obvious, right? Cars that have really low center of gravity, like, you know, Honda Accord, for example, are very, very unlikely to tip unless you go extremely fast, right? Okay. Any questions? Yeah, compared to a truck like an F-150 or something like that. Or a semi. Yeah. Okay. So that's also why... Do you guys know where in like Teslas, do you know where the battery is? The battery is like the heaviest thing in the car, I think. It's on the bottom. Yep. It's on the bottom. It's like very like wide and flat. Like thin like a rectangle. And yeah, it's on the bottom. So it keeps the center of gravity really low. All right. So next problem we want to do is this one. Tesla for 25K. Wasn't there a model that he was going to release that was supposed to be kind of like pretty easy to afford? Yeah, I don't know. I think it's more likely that you're going to see... I mean, the electric cars still haven't met like mass adoption yet, right? I mean, I think less than 1% of people on the road are driving electric cars right now, maybe. Maybe it's higher than that. As that number gets higher and more of the population is buying them, the price should become pretty affordable, you know? It's just like, it's like anything else. Prices always come down. You know, the PS5 is really expensive right now, but it'll get less expensive later, right? But the things that everybody uses, like cars, they basically have to come down in price or no one will ever buy them, right? And electric cars can't really have much of an impact on our economy or on the environment unless they get cheaper, because like I'm not buying one that's that expensive. Like my car from 2003 works just fine. Like it's just fine. I'm trying to compete with there's other companies that are competing with Tesla. There's other companies that are competing. They're maybe just a few years behind, but they'll catch up. Like no company can like maintain a dominance in the market like that for too long in one sector or whatever. You'd rather buy a Honda Civic than a Tesla? Yeah, man, Civics are great. Really good gas efficiency. You know, they last forever. I mean, you could have a Civic from like 1993 and it probably runs really well. I have friends that have cars like that. They've had them their whole lives. They like got their first car in high school and they've had the same car their entire lives. Like, I don't know. I mean, cars just get you around. Yeah, 300K miles, still great. Yeah, exactly. My car has like 200,000 miles on it. It's a Toyota Camry. Runs great. It's no problems at all. All right, so, you know, having nice cars is nice, but they're also really expensive. I had a more expensive car when I was younger. I had a BMW, and oh my god, they're expensive to repair. So eventually I had to get rid of that thing. Okay, so a governor is made of a 1 kilogram ball attached to 10 centimeter rods as shown. The lower collar is free to slide up and down the frictionless lap. So what we have here is, I guess this top piece is fixed. But there's a ball right here, and there is a kind of a sliding connection point right here, and then 2 strings. There are strings, right? Actually, these don't have to be strings. These could just be rods. Actually, they're probably rods, honestly. These are rods. And then this one can basically slide up and down, and then I assume that this object on the end has like a hinge or something, so that the angle that's made between these two here is adjustable. So you can imagine that this piece can move up or it can move down. So we want to figure out basically, it says the lower collar is free to slide up or down. when the shaft has an angular speed of this, the two colors are exactly square root 3L apart as shown. We want to find the tension in the upper and lower rods. So the tension here and the tension here, that's what we're trying to find. There's going to be two of them. Now, one thing that's mentioned here is angular speed. And I haven't talked about what this is yet, but I'm going to describe it right now. So when you're talking about an object that's traveling in a circle, okay, so let's say we take something really simple like a ball and say that it travels in a circle. And let's say it does so with a constant angular speed and a constant uniform speed. So we say v is constant. Then when something moves in a circle, we can describe certain things about its motion. And one of the things we could describe, for example, is the period. So we use the symbol t to represent what's called period. Let's call this r. And period is basically the time for one revolution. And one revolution is all the way around one time. The next thing that we can define is what's called angular speed, I guess would be the next thing to describe. And angular speed, we use the symbol omega. And, okay, so angular speed, sometimes called angular velocity as well, depending on how we're talking about it. And angular speed is basically the number of radians per second that the object travels through. So if an object goes around one time, and we want to calculate kind of the total angle that the object has rotated through, what would the total angle be that the object rotated through? Maybe to make that question a little bit more clear, what I could do is I could say, suppose the object rotates from that point to this point right here, and we say, okay, when it gets to this new position, it's rotated through an angle theta. Yeah, the answer is 2 pi, or 360, that's right. Then the question would be, if it rotates back around one time, what angle would it rotate through? Yeah, and the angle would be 2 pi. So you go through 2 pi radians, right? In one revolution. Right? 2 pi radians basically corresponds, I'll just write this up here, 2 pi radians is equal to one revolution. One rev. So if I take 2 pi radians and I divide by the period, which is the time that it takes for one revolution, then that's what gives me the angular speed. There's one other thing, which is called frequency. And frequency is basically equal to 1 over the period. And frequency is usually measured in like revolutions per second or RPM. This is the way it's measured in cars. Revolutions per minute. That's frequency. Okay. Angular speed is measured in radians per second, and then period is measured in seconds or minutes or hours or whatever. So what's the period of the Earth's rotation on its axis then? How much time does it take for the Earth to rotate one time on its axis? "24 hours, right? Yeah. That's that's Earth's period on its axis. What's the period of the Earth's rotation around the sun? How much time does it take for the Earth to revolve around the sun one time? 365 days and a quarter, right? Okay, so you all have 365 and a quarter. That's why we have leap years, Andrew. It's not exactly 365 days, and if we didn't take into account for that, then the seasons would basically be off by 1 day every 4 years. And before you know it, after 50 years or so, all of a sudden, like summer doesn't start until like August or something like that, right? And then lasts until November. And you wouldn't notice this kind of stuff out here in California because it's pretty much the same, weather most of the year. But yeah. Anyway, okay, so you're all pretty, used to these concepts of period, but maybe you didn't use that word before. So it's just the time for one revolution. Okay, so angular speed in this case is given as 324 over pi RPM, which... Okay, I didn't write this problem, but certainly this means... Normally RPM means revolutions per minute, but... I think it means radians. So I'm going to write this as omega is equal to 324 over pi radians per minute, I guess. It's kind of a weird way to write it, isn't it? I've done this problem before, but that never really bothered me. It says angular speed, though. I'm sorry, give me a moment. Let me turn my heater off. Okay. So, alright. I think we're good here. Now, we can make some connections. I didn't make all the connections here between velocity and all of these topics here because we know that the circumference of the motion is 2 pi r. And the period of the motion is t. So this allows us to find what the velocity is equal to. 2 pi r divided by t. And since 2 pi over t is equal to the angular speed omega, then we can say omega times r is equal to the velocity. Which also means we could do one other thing, which is that we can take our equation, which was v squared over r, and we can write it using omega, because now it's going to be omega squared r squared divided by r, which means that this ends up being equal to, I think it's r squared omega squared, right? So this is another definition of what centripetal acceleration can be, is r times omega squared. Okay, so I think we have enough to solve this problem. Now, what we need to do first, let's go back to what we're doing. So here's our picture. This object is rotating in a circle, so it's going around in a circle like this. That means it's going to have a centripetal acceleration that's going to point towards the center. And in order to figure out the tension in these rods, we're going to have to draw a free body diagram. So let's do that, maybe right here. So what are the forces that are acting on the ball going to be? That's what we're looking at, is the forces on the ball. What forces is it going to experience as it's rotating around like this? Weight and then 2 tensions, that's right. Okay, so one tension force is going to go up like this. One tension force is going to go down like that. Whoops. One tension force is going to come down like this. I'll fix the angles in a second. There's also going to be a weight, right? The weight's going to come... Oh my god, I hate how it does that. If you move it just a little bit, it'll start. The weight's down like this, right? Anything else? I think that's it, right? So... Let's fix the angles and stuff here. Alright, so we've got our 2 tension forces. One this way. Stop it. And then one, stop it, click, move, there we go. So one tension here, one tension here. We don't really know how they're related to each other. And then a weight. Now I'm going to call them, I'm going to give them different values. So we'll call this one T1, and we'll call this one T2. I think where I'm going to write that is like right up here though. So we'll write T1 where it is, but we'll put T2 right here. And then here's our weight pointing down, so I'll just write mg. And then normally other things we need to do on here is I need to define a coordinate system. So the coordinate system is going to be positive radial direction this way, because that's also the direction of the acceleration. And then I guess up can be positive y. Okay, and the direction of the acceleration, we should throw that on the picture too. We'll say it's accelerating this way. There we go. Okay, after we've done that stuff, we need to break up our forces into components, so let's do that. So we're going to have components for T1 and T2. So T1 is going to have a component that goes this way, and another component that goes this way. So if this is T1, then we're going to need an angle here, and I guess the angle that I'm going to choose is going to be this one. We'll have to calculate what it's equal to. So let's call that angle right there theta. Then this side is going to be T1 times the sine of theta. This side will be T1 cos theta. For T2, do the same thing. Use a different color. So T2 is going to go this way, and then this way. And if that angle is theta right there, then this angle is going to end up being theta 2. So this side is going to be T2 sine theta, and this side will be T2 cos theta. And now we can use our equations, which say that net force acting in the radial direction should be equal to mass times acceleration in the radial direction, and then net force in the y direction, I'm going to say, is equal to mass times acceleration in the y direction. Up and down is y. We're going to assume the bead maintains a constant elevation. So we're going to say this is equal to 0. So in our radial direction, we're going to have T1 times the sine of the angle theta plus T2 sine theta is equal to MAR. Now I'm going to use this definition down here because we're given omega for AR. So we're going to put R times omega squared. In the y direction, we have T1 cos theta pointing up, T2 cos theta pointing down, mg going down as well, all equal to 0. And now I think we have all the information we need because we're given the mass and we know the angular speed. We're going to need to convert this to radians per second, actually. But we should be able to solve now for T1 and T2. Oh, we do need to find the angle as well, don't we? So what is the angle? So what we have is a triangle where one side of the triangle, I guess we're going to have to use shapes. So one side of the triangle is like that. And we have another side over here. And another side here. We'll just fix it. So there's our triangle. Make it a little bigger. And the information that we're given is that this side of the triangle is 10 centimeters. And that's called L. And then this side over here is basically the square root of 3 times L. And what we need to find is an angle, and I think the angle that I was using was basically this upper angle right here, right? Theta. So the angle theta, I don't know where I could write this. Let's make our picture here a little bit smaller. Okay. So then our angle theta, L over 2, thank you. Yeah. L over 2, because this is split in half. Thank you. Square root of 3L is the whole distance. Thank you. So it's square root of 3L over 2. Appreciate that, Chris. Thank you. Let's see. So theta should be equal to the arc cosine of basically square root of 3 over 2, right? Because it's going to be basically this side divided by this side. So the L's will cancel. So we end up getting, I think that theta is going to be equal to 30, right? Okay, so we know what theta is. And I guess let's go ahead and let's convert this as well. So if we have, let's do a different color. So if I have 324 over pi radians per minute, I have to, what, multiply this by 60? Because there's 60 seconds. No. We're dividing by 60. 60 seconds in a minute. And I just want a number. I don't really care about 324 over pi. I just want a number. So omega should be equal to I get 1.72. Okay. So, what were we trying to solve for? The tensions, right? So we really just need to eliminate the tension from one of these equations here. Doesn't really matter how we do it. I guess what I would normally do is just multiply the left equation times cosine theta and then add it to this equation. But it doesn't really matter how we do this. I guess we could just solve for t1. Let's just do the substitution method. That seems to be the way that students are often most comfortable with. So t1 sine theta is equal to mr omega squared minus t2 times the sine of theta. So if we divide everything through by sine theta, we're going to get t1 is equal to that, because both these terms have a sign in them. If I then plug that in for t1 into this equation here, we are going to get So I did two things in this step. I added the mg to the right-hand side, and I plugged in this expression for t1 in for t1 here. It's multiplied by cosine theta, so I also distributed a cosine theta 2 through. So we'll have cosine theta times the first term, and we'll have a cosine theta times this. You'll get negative t2 cos theta, so you get two of those. And we just want to solve for t2, right? So we're going to end up getting, let's see, it looks like, and I'll do it like that. I don't like doing it this way, but I will, just to be more clear. So negative 2 t2 cos theta is equal to mg minus mr omega squared over tan theta, because cosine over sine is the inverse tangent, or is cotangent. So we write it as 1 over tan. And then we just want to solve this for t2. So we're going to get, oh, you know what? Actually, if I leave it like this, it actually will come out a little simpler, won't it? Okay, so now we divide through by negative 2 cos theta. So we're going to get t2 is equal to, I'm going to scroll down just a little bit, so this is the bottom of your screen in case it's blocked for some reason. T2 is equal to, I'm going to divide the negative through, which is going to invert these two. So we're going to have m times r omega squared over sine theta minus g over cos theta, and it's all divided by 2. Does that look right? Okay, so m over 2 was, 1 kilogram multiplied by, R. We never actually said what R was equal to. So R would be this, right? Because it's this triangle right here. And R is the bottom side. So R is going to be equal to probably 5 centimeters, right? Yeah. R is equal to L times the sine of 30, which is equal to 5 cm. 10 cm, angle's 30, the side is... It's also a 30, 60, 90 triangle, so... Okay, so R is 5 cm, which is 0.05. Times omega, which we said was 1.72. Squared. Divided by the sine of theta, sine of 30. Minus g. Everything's in meters now, and kilograms and stuff, so we can put in 9.8. And then divide that by cos 30. Now, hopefully this is a positive number. If it's not a positive number, then I made some kind of algebra error somewhere, or a calculation error. That does not look like a positive number to me. What do you all think? I'm pretty sure that's going to be a negative number in the parentheses there. I mean, I divided by -2. If you look at the algebra, I did that. Something just feels wrong about the way that I solved this. Yeah, there's no doubt it's negative. I mean, look at the numbers. This is 10 divided by 0.866, so this number is going to be like 12. And this number is 1.7 squared, which is like 3. So 3 times 0.05 is like 0.15. It's not even close. This number should be the one that's positive. All right, what did we do wrong? Let's see what we did wrong. I'm actually worried about this part. Like, I think this number may have... I've done this problem before, though. I've never seen this. I've never had this problem before, so I'm guessing. Okay, it's possible I made an algebra error, but this bothers me. This omega equal to 324 over pi RPM. Let me look at the notes. Something's weird about the way that came up there. No, it just says RPM. I think that's supposed to be a frequency. Because then the RPM, the radians per minute, would be 2 pi times this. And if it's revolutions per minute, yeah, it'd be 2 pi times this. So it'd be times 6. Which would mean that our answer for... wait, no, not that. Just one note. Which would mean that our answer for this would be 6 times as big. And then this would work out. But let's just make sure we didn't make any other errors. Did anyone see any other errors that I made? Yeah, the fact that it says RPM, that was really like an alarm bell for me. I think this is supposed to be frequency. Because this over here is where I was saying that frequency is measured in RPM, right? Ultimately, it doesn't matter. These are just numbers, right? So I think that the physics is right, but let's just check. So tension this way, tension this way. Tension 1, tension 2. The ones that point inwards are going to be times the sine of theta. We said this side was 10, this side's root 3. So the angle ends up being 30. Okay. This one should be these two forces because they're the two forces that are pointing inwards, right? So we solve this, we subtract this one over here. You get T1 sine theta is equal to mr omega squared minus this. Divide through by sine theta, so this term gets a sine theta in the denominator. This one doesn't, because it cancels out. You take all of that and you plug it into this equation. Let's just make sure this equation's right. So T1 was the upward force. We said T1 minus T2 cos theta minus mg. We plugged in for T1. T1 was all of this stuff. Mr omega squared here minus T2. Well, someone's typing. Maybe they figured it out. That looks fine. You have to multiply both terms by cos theta. And then we have negative 2T2 cos theta. So we basically need to divide all the right-hand side by 2 by a negative sign. When you divide by a negative, it flips the direction of these two, which is what I did. I didn't do that. Oh, I did do that, yeah, because g became negative, right? Oh. Oh no, the mass is on the outside. I factored the mass out. No, Calvin, when you divide by negative 2, I mean, we're going to get the same answer. I'll just redo it, but we'll get the same answer. It doesn't matter how you do it. So look, let me just redo this step right here. So that was the answer we got, right? Let's see if I redo it, if we get something different, if I do it a different way. So basically we have to take this whole thing and divide by 1 over negative 2 cos theta, right? Right? The whole thing. So what we'll get, I'll just move this down a little bit because I don't like writing in between there. So what we'll get, on the left-hand side, we'll just have T2, right? On the right-hand side, we're going to have mg over 2 cos theta, and it's negative, plus, because negative, negative, mr omega squared over 2 sine theta, which is equal to m over 2 times, now just flip the order, r omega squared over sine theta minus g over cos theta. And that looks exactly like what we have down here, right? I didn't do anything wrong. I mean, normally I do something wrong, and I wish my math was wrong. Actually, I wish my math was wrong because I don't like the reason being that this question's confusing and that this is actually frequency. It's not angular speed. But that has to be what it is. I mean, the other option is that it's angular speed, but it's measured in revolutions per minute, which is a possibility. Because if that's revolutions per minute, then we just have to multiply by, 1 revolution is 2 pi radians. And we'd be dividing. No. Yeah, multiplying. Yeah. I think that this is just in revolutions per minute, actually. I think that's the error that I made. So we got to go back and fix it. So you're not going to see your angular speeds written like this, by the way. It's just not how it's going to happen. I think this was actually supposed to be revolutions right here. And we canceled out the minutes, but we didn't cancel out the revolution part. So we needed to divide, we needed to use we needed to use, I don't know where it is, that right there. That's what we needed to use. 2 pi radians is 1 revolution. So that's what we did wrong. So that means that our angular speed, instead of being 1.72, is going to be like much bigger, which will solve the problem. So what I get then is 324 divide pi divide 60, and then times 2 times pi. Now I get 10.8. See, that's the number I remember using for this too, so I knew something was wrong about that. So this is 10.8. And then when we come down to our final result right here, we just need to change that one number right there. I'll put it in red so it's clear what we did. So this is 10.8 radians per second. And now, even now, it's 10 squared. Even now, it looks like it's going to be negative to me, but maybe I'm wrong. So 10.8 times 10.8 times 0.05 divided by 0.5 minus 9.8 divided by, oh, this is going to be really close to negative to me. It's not negative though. Divided by 2. So I got 0.174 as my answer. It was almost 0 actually. Really tiny number. And then if we want to find T1, do you all agree? Do you get the same number as me? Okay. T1 then is mr omega squared over sine theta minus T2. It's pretty much just going to be equal to this. So 1 kg multiplied by r, which was, I think, 5 centimeters, so 0.05 meters. And then times omega squared, which is 10.8. Sorry for being so confusing. I know physics is hard enough without me making all these mistakes. So 0.05 times, oops, 0.05, oh, minus, I left off that part. So 0.05 times 10.8 times 10.8 divided by 0.5 minus, so I got 11.5. And it looks like the bottom arm is the one that has all the tension in it. However, if it were to go faster, then T2 would get bigger, but T1 would get smaller, I believe. Because, for example, if we doubled the speed right here, T2 would definitely get bigger. But as T2 gets bigger, then T1 also gets a little bit smaller. Although, this number would get bigger too. But anyway. There we go. Anyone have any questions? Theta. Why we didn't... Sorry, Chase, just give me 1 second. Let me answer this question from Miguel first.
Oh, I was just questioning about the 10.8 rads, that's all.
Can you explain the theta part? I'm still confused why we didn't divide by 10. Which, this part right here? Oh, this part. Yeah, sure. I left out a step. So, the angle theta is the arc cosine of this side over this side. So really what I did was arc cosine of root 3 L over 2 divided by L. That's what I did. The L's canceled. Okay, and you're asking about the 10.8, Chase? Right here? What about it?
Oh, it's like... Oh, never mind, I see it. I just forgot to put that in.
Well, I went back and had to recalculate it, so if you weren't watching, you might have missed it, so it's understandable.
Alright, I'll take a picture of it.
Okay, any other questions? Okay, what I'm going to do is